Now, let's recap what we talked about in the last class lecture. We talked about flaws or slip planes or line defect dislocations with edge and screw dislocation, and in this class earlier we talked about grain structure also. So, just to recap, you have dislocations. You think about this plane here, which is actually this plane here, which is actually the slip plane or the plane along which the deformation is happening or slipping is happening. And just wanted to tell you about the slip plane because the next discussion is generally associated with this. And in the other drawings, we used to notate this as a using a perpendicular sign, okay, in this, and then here you have a rotation sign there. Anyway, now how these slip planes, flaws and grain structure influence the mechanical properties. They do have an influence on mechanical properties, and flaws and these defects, line defect or like edge dislocation or screw dislocation, etc., can be the weak locations within the bulk material. Okay. Now, they because they tend to be weak, they actually tend to decrease the strength of the material. If there is a lot of defects in the material or flaws in the material, voids, cracks, etc., present in the material, then the material in general will have lower strength, and also it might reduce the toughness. Okay. Now, this is all associated with the energy required to propagate a crack. If there is a flaw, we can think it as a crack, micro crack maybe, but then there is some energy which is required to make sure to propagate that crack. So, that energy is what is most important thing when we talk about toughness, or even in strength case also that matters a lot, because once the it has to lead to the fracture behavior. So, now grain boundaries can act, I mean here we are talking about the true stress at which the material fails, etc. Okay. Now, grain boundaries can act as crack inhibitors. Okay. So, let us look at this drawing here at the bottom. This again I got it from the internet, but you can see here there is an incoming, you see this perpendicular sign here, right. Now, this is if the force is applied like this, there is an incoming dislocation. So, this dislocation will keep moving towards the right, and at the grain boundary there will be some stress release, or because the alignment is not same as on the left side and on the right side. The right side the alignment is slightly different. So, because of this change in the alignment, there is some the direction changes, direction of movement of this slip of this dislocation changes. So, dislocations first they try to accumulate over at the grain boundary, and then they start moving in this direction along this slip plane. Okay. So, you have two things here, incoming dislocation and outgoing dislocations. Okay. So, if it was going in the same direction, probably you would need less energy. If it is in the same direction, then the energy requirement to move that dislocation would be relatively less. But this is what is kind of a useful thing about the grain boundary, because it helps in enhancing the toughness and probably strength also of the material. Now, effects of slips and grain boundaries, or I am going to call grain boundary as GB here, on toughness and ductility. Now, atoms at the grain boundaries are at higher energy state. When we talk about atoms which are at the grain boundaries, they are at higher energy state than a particular atom within the grain boundary. Now, slips are blocked at grain boundaries. So, we just show that drawing earlier. Same drawing I have repeated here. So, the slips are blocked, or because the grain boundary acts as a crack inhibitor, or it stops the crack from progressing. Okay. So, they are blocked at grain boundary, but then as you apply more stress, there will be a point at which it starts moving in a best possible direction, through the next grain or adjacent grain available. Anyway, this process requires more energy because you have to cross through that grain boundary. You need more energy to deform the material. Now look at the drawings here. You can see this is an incoming slip plane ISP, an outgoing slip plane OSP. So you can see here look at the direction of these arrows. So these perpendicular symbols are actually the edge dislocations. Now in this sketch B, you can see that there are multiple movements possible. This is one outgoing slip plane and this is the another one, and here it is happening along the grain boundary also. Okay. Now there is a third one where this point, so in the second one this point was same, and in the third one there is a slight movement. So this moves like a zigzag way. It comes this way and then goes like this. So again, that might need more energy than the case in case B. So C might need more energy, and in C, then again another case which is B, here also you have movements in multiple directions. So these all are associated with different levels of energy requirements to continue to deform the material. Okay. So because of this, the size of the grain boundary has an influence on the toughness. We can say that. Okay. Now here, when you look at the left side micrograph, it's like, this is 100 microns. The length of this little straight line is about 100 microns. So you can say the size of this is 1, maybe 2, 3, 4, 5, 6, 7. Let's say 8. 0.8 microns is the distance from this point to this 0.8 millimeter, sorry, 0.8 millimeter. Now, so you are looking at within a centimeter in size. This one image is within 1 millimeter, not centimeter, within 1 millimeter in size. Okay. Now, on the left side you have larger grains as compared to the image on the right side. Now, when you have larger grains, if you have a crack along the grain boundaries, or this is the intergranular crack. Okay. If I measure the length of this red line, if I try to measure the length of this, red crack, the red line indicates the crack, the one on the left side will be shorter than the one on the right side. This is less and this is more. Okay. Because when you have larger grain size, the actual length, if you just follow the grain boundary, the actual length, not the displacement from one point to the other, but the actual length from one point to the other, it will be more in the case of a smaller grain size, that is this, than in this case. Okay. So, larger the grain size, shorter will be the length of the grain boundary. Now, when you have shorter length, that means the energy required to move a dislocation along that would be also relatively less. Okay. So, message here is, smaller the grain size, the more will be the length of the grain boundary and hence more toughness. Okay. So, these are mainly for hot rolled metals. Okay. If you actually do cold rolling or cold drawing also, this is the two different major way by which we do cold working. There is a common term, cold working or strain hardening, etc. So, cold rolling, where you have two rollers here and the material is coming out through these rollers, whereas in case of cold drawing, you are actually pulling the metal through a die, which is probably this is a die, and then you can see the change in the dimension or reduction in the dimension as the material is pulled through that. Okay. So, cold rolling and cold drawing, these are two different processes, but the objective is kind of similar. And mainly to increase the yield strength. That is typically what we do this for. So this process changes the way in which the microstructure is, and in general what happens is with increasing cold work, the hardness and strength increase, okay, and the ductility decrease. So hardness and strength increase, it is probably a good property which you want, I mean depending on the case, but decreasing ductility is usually not a good idea, because then it becomes a brittle material, and brittle material will have catastrophic failure in nature, so which we don't want. So we want to maintain that ductility or increase the ductility, the lost ductility. How do we do that? So to restore ductility, we do heat treatment are done during the manufacturing itself. So cold drawing is done to increase the strength or yield strength or even hardness of the material, but in that process the material loses ductility. So to regain that or restore the lost ductility, there is some heat treatments which are done. Okay. Now heat treatment, it can actually, what is the idea? This, when you do this heat treatment, it changes the grain size to a desired level as you want. So two major way of heat treatment which I am going to discuss here briefly are annealing and hardening. Okay. So in case of annealing, what we do is we heat the material and then allow it to cool in a slow manner. Heating and then slow cooling. And in case of hardening, it is heating but cooling is very rapid. Okay. So heating and then slow cooling, here heating and then very rapid cooling. So you can see the slope in the second phase is relatively less. So, okay. Now because of this slow cooling and rapid cooling, the final grain size is going to be different. Now anyway, let us look at the annealing first. You have heating and then slow cooling. Then what happens in this process is, when you heat the material, the large grains which are present, they tend to break down, and then as it progresses, it allows a little bit of grain growth, means a new set of grains are formed, and which could be larger in size. Okay, that depends on the rate of cooling. So you are basically rearranging and this happens not in a molten stage, this happens after the solidification after the material solidifies. Okay. So grain growth, so you kind of rearrange the grains to a desired level of grain size. Okay. Now in case of hardening, it is heating and then rapid cooling, and this also breakdowns in the heating process, it breaks down the existing large grains, and then because of rapid cooling, what happens is the final grain size is going to be relatively smaller as compared to the case in the annealing case. Now when you have smaller grains than in the annealing case, you might expect it to behave in a different way. Why? When you have smaller grains, that is this case, here you have larger grains finally. Now this hardened one will need probably more energy to deform or crack, etc. Okay, because of the length of the grains. But again, these comparisons, when you look at more ductility, less ductility, etc., you should look at the grain size for the same material, not for different materials. You can't compare like that. For the same material, if the grain size is more, then you will have low toughness. If the grain size is smaller, you might have higher toughness. Now generally when we look at this, you can see that heat treatment generally tends to increase the grain size from the cold work stage. So okay, from the cold work stage. So this is cold working stage, and then this is after the heat treatment. Okay. Now look at the graph on the left side. You can see recover. So this is the increase in temperature. Okay. Okay. Then there is a recovery happening here, and then recrystallization, and then the grain growth. Okay. Now, slightly grains recover slightly from cold working, that is the recovery stage, and then the recrystallization temperature when it gains, and then you cool it down. Okay. So, that is what is happening. So, the grain growth is allowed. So, here you can see, look at the dislocation density, first thing to look at. You can see here there is all these light gray lines, they are the dislocation present in the material. Okay. Now, you have this dark lines here, these are all dark lines which kind of indicates the grain boundaries. Okay. So, you can see several grains over there. Now, what will happen? The residual stress, so the dislocation density decreases as you move to the right, and then as you keep heating the material, and then internal residual stress, you can see here, this decreases as you going through these 3 phases. Okay, residual stress. Now, look at the major properties, which is hardness. Hardness in the beginning, the cold work stage. So, for some time there is no change, but when the recrystallization happens, definitely the hardness is decreasing. You can see here the hardness in this region is decreasing, the green graph is going down. Okay, and then it remains kind of stable after that. See, most of these things, if you are taking a graduate level course, we will go more deeper into this, but here my idea is to just to give you a flavor of very superficial way, but of what happens when we talk about heat treatment. You should know what is heat treatment and why it is done, and what really is achieved because of heat treatment. Now, looking at the strength, this brown graph here. In the recovery stage, not much difference, but again in the recrystallization stage, you lose the strength. Okay. Now, after the recrystallization, there is in the third stage, grain growth, you have again similar strength. Now, you can say that you do not want to reduce the strength, but that is the metallurgist's job of finding a material combination where strength loss need not be very high, or see, at the end what you want is, at this point you need sufficient strength, sufficient hardness and sufficient ductility. That is the objective, let us say. So, as long as all these properties are sufficient in nature, then it is okay to use that material. So, you do not, just because one graph is going downward, you do not need to get worried about it. So, point is, so over here these two are the strength and hardness, if they are sufficient, that is fine. Now, here ductility, if they are sufficient, that is fine. So, you always have this requirement of these parameters. Hardness, how much it should be, ductility, how much it should be, or minimum, strength, minimum, how much it should be. All that are the target properties, or target values for these properties will be given at the time of design, and then the steel manufacturer has to adjust his adjust the material combination or the composition of the material, I mean the raw materials which is put in the molten material, and then all this manufacturing process or the cooling rate, or how many times you do this heating, cooling treatments, etc. All that have to be fine tuned so that you get these target properties, okay, this and this. Okay. So, change in the grain size can change various properties of the material, that is a big message, and grain size can be changed or controlled by having a heat treatment even after the cold working process, or cold drawing or cold rolling process. You can make the material to go through some heat treatment so that you get a desired grain size, and then Because of that, the properties can be engineered. Okay. Now, let us go into the fourth type of defect, which is volume defect. We started with point defect, then we talked about line defect, then we talked about the surface or plane defect, that is grain boundaries, and then we are now going to talk about volume defect, which are mainly voids and inclusions. Voids means air void, there is no material present. Inclusion means there is a foreign material which is present inside the parent or inside the bulk material. Okay. So, you can see this picture micrograph on the right side, you can see the size over here, there is a white line and that is 10 micron, that is 0.01 millimeters, so small, right. Now, this is one we can say an inclusion inside a material. So, this region here is the bulk material and this region, and this I can say as the inclusion, okay, the center one. So, this one. Okay. So, like this, this is a very close up view, so to make you understand, and then these materials are considered to be external to the typical phase of the material, that is this region here. Okay. They are not really interacting with them, and if you say void, there are small pores left incomplete or just some space is available. Inclusion is regions of a second phase contained wholly within a grain. Okay. So, if it is clear now. Now, effects of voids and inclusions on material behavior. So, look at the 5 images here, 1, 2, A, B, C, D and E. And what is happening in the A case? You have these inclusions or voids like this one, okay. So, lot of these black dots which you see here are all those inclusions, or even voids, we can say same thing, but let us talk about the inclusions right now. Now, as you keep applying this tensile stress, you can see the black arrows on each of those drawings. As you apply this stress, what will happen is, here you can see there is this, this particular portion getting elongated, it is getting elongated this way, okay, and then void inclusion is there. If you go back into the previous thing, you can see this space here, okay. So, we can similarly, so as I pull, it gets detached, that inclusion gets detached, and then you have a stretching happening here. Here also you can see, here you can see the other way. Here you can see it is getting pulled this way, right. So, like that this deformation happens. So, eventually you have this stage as in C, where these voids start growing. So, here you have this and you have this, it is growing here, okay. Now, eventually after some time, what will happen is they will grow in such a way and then try to join kind of. So, onset of necking, this is where the necking kind of happens. So, there is a flow of material which is happening at this stage. So, you can see this region, this shaded region, they get kind of connected, or the voids tend to become one large void and eventually they crack. So, that is your crack or coalesce, and then cracking happens. Okay, cracking or even fracture. Happens. Now, these are some real examples of the first picture is a microstructure of grey cast iron. You can see in the cast iron you have a lot of these flakes present. You can see this is another flake, this is another flake. Okay. In this picture you have 3 big flakes of graphite present. You can see here graphite. So, this is an image of an alloy of iron and 4% carbon. So, cast iron has a lot of this carbon present, 3 to 4% easily. by weight. The microstructure has two main constituents. The long pale regions are flakes of graphite or carbon. Okay, you can say this is that this long. So these are the reasons for the brittle nature of cast iron. Okay, so these are the reason for the brittle nature of cast iron. And because when there is some force which is applied, actually what will happen is these crack will kind of follow the path of these flakes, or their stress concentration will happen at one end of this maybe here, or so along this graphite flakes you will have some stress concentration, crack will kind of propagate through that. Now this is the reason why we don't use cast iron in many structural applications, because we know that the failure is very brittle in nature and you don't really see deformed structure. We already discussed this in the previous lecture. So we have materials like ductile iron, which is having some inclusions and it has a little bit more ductility than the cast iron. So inclusions, rather than having flakes like this, the ductile iron will have inclusions, spherical inclusions. And here you have a picture of mild steel on the right side, where you can see carbon steel, or the general name is mild steel, with 0.1% carbon, much less as compared to cast iron. Cast iron is 4%, and mild steel, here this particular case we are talking about 0.1%, very very small. And it has two major constants, ferrite, which is the light colored region here, let's say I am going to call it F, and then perlite, which is this particular region, the darker shaded region. Okay, the small spots within the ferrite, within the white space, these small spots which you see, a lot of them are spread widely in this ferrite phase, or the light gray phase, are inclusions or impurities such as oxides and sulfides. So whatever inclusion or impurities are present there, and when this will have an influence on the failure pattern, etc. This can have an influence on the failure pattern, because they tend to behave like a weak point when the load is applied. Now let's talk about alloys. What is alloying? It's a process in which two or more metal elements are melted together in a precise combination. So not just mixing, but in a very precise combination to form a specific material with certain target properties. Okay. Now there could be properties like it should be malleable, like the ability to flat and then it could be you need to have an increased strength, sometimes high ductility, malleability, weldability. So many of these properties need the corrosion resistance, or sometimes we might want the material to be very shiny in nature. Many properties are targeted. So whatever, based on the target properties, we will include other elements and mix them properly with the in a combination, and that process is what is called alloying. Now in general we can say material manufacturing process, MMC I am calling here, melted. First it is melted, materials are melted and then mixed together and then finally cooled. Now various liquid and solid phases exist, and we are going to call them different phases, solid phase or liquid phase, depending on the rate depending on the absolute temperature at that time in this cooling process. So here just a picture to show different type of metals, and each of them have different properties. Okay, it's not that all metals are of same property, like all steel need not be of same nature. Sometimes you will need steel even for construction. Sometimes you will need steel which is very ductile in nature, especially when we talk about earthquake resistant structures. We want steel which is ductile in nature. We don't want it to be very brittle in nature. So how do we make such highly ductile steel? So it's essentially to do with the way you make steel. So, I will cover that in the next in the module on steel, but just to briefly tell you that these are all very important for civil engineering construction also. You need to be aware of, as a civil engineer, some of these things must be known to you. Okay. More detailed stuff is for metallurgists, but we should know what is how in general stuff of this grains, etc. Now, here is an example of some major alloys which we use: brass, bronze, solder material, stainless steel, etc. So, copper and zinc where they are used, and then copper and tin where they are used. I will leave it to you to find out the reason or what are those properties which we are targeting, and then accordingly. So, you can do some homework in that line. It will be good to know what are the properties for various type of uses. Okay. So, properties, I am going to call it target properties, okay, for various types of uses. Now, phase diagram. So, we just discussed about different phases here, right. So, various liquid and solid phase might exist depending on the temperature at which the material is. So, this is generally understood by something called phase diagram. So, phase diagram exhibits the relationship between the material composition and transition temperature. So, composition versus transition or the temperature is what is essentially the phase diagram. And these transition temperatures depend on the material composition. So, it is not that the transition temperature is same for all materials. No, it definitely depends on the combination of the materials or the mixture proportion of the material. So, more ideally in the first, here I am showing only temperature and composition, but that is not the only thing. Ideally speaking, a phase diagram is a graphical representation of combinations of temperature, pressure and composition. Okay, it is here not only temperature, but plus pressure also will come. Okay. So, temperature, pressure and composition. So, or even other variables if you have something for which the specific phase exists at equilibrium. So, this is what is a phase diagram. We will very briefly talk about this phase diagram for water. So, this is how typically it look like, and you can see here there are orange region and this purple color region, and then you have the green color region. So, one is for solid, then liquid and then gas. Okay. Now, you can see if you follow this border between each of these phases, you can say at that border, at that point, when there is a slight movement, slight change in either pressure or temperature, the phase will change from one to the other. Okay. That's so, for example, here if you say on this, if I take this curve here, okay. So, a slight change in the temperature that is moving in the horizontal direction. Let me draw it more closely. Let us say here a slight change in the temperature along this red line, the small red line which I just drawn. If the temperature slightly increase at the same pressure, if the temperature slightly increases, then it will condense. If the temperature slightly decreases, if the temperature slightly increases, it will vaporize, and if the temperature slightly decreases, then it will condense. So, you can have C condensation and then V vaporization. Okay. So, like that also happens between solid and gas, that is sublimation and deposition, and between solid and liquid, melting and freezing. So, we are going to look at this solid and liquid in the next slide, but before that I request you to watch these YouTube videos, very good. This is actually on water. You can see ice crystals formation, boiling water and also gas bubbles, bursting of gas bubbles. All these things are visible at the same time. It happens in the same petri dish which is used in this experiment. So, all three kind of coexist because of just slight because while in the experiment in the same dish, different locations in the dish or the H2O in the different locations in the dish experience different combination of pressure and temperature, and then slight movement in the pressure and temperature leads to this change in phase. So please watch this video as an assignment. I am telling, please watch this video, it's very interesting to see. Okay, now binary phase diagram for two soluble materials. This is one of the simplest phase diagram which we are going to discuss here, and you can see here again this is the composition. Okay, composition. Here you can see the same thing for material A at the top axis and then material B at the bottom axis, material A and material B. Okay. Now that means if I draw a line along this, I have 25% material B and 75% material A is the composition. Okay. So now the temperature increases on the axis, you can see. So here this means the material changes from at this temperature, it starts melting. Okay, that is the melting point of which material? Of material A, because at this line you have only material A, it is 100% A and 0% B. Now if you go to the right end of this graph, this is 100% material B and 0% material A. Okay, so this clarity should be there, because this A, it's increasing towards left and B, it is increasing towards right. Okay. Okay. Now, so this is melting point of material A. Similarly, you have melting point of material B here. So that means here it is liquid and here it is solid. Okay. So I think that is clear now. Now there are also phases which are having both liquid and solid. So this curve here is called liquidus. That is kind of the boundary between the liquid 100% liquid phase and the liquid solid phase. And here you have solidus at the bottom, or this curve here is the solidus, which is 100% solid at the boundary between 100% solid and the solid liquid phase. Okay. So this is about the three areas in this. You have a liquid phase, you have a solid phase and a liquid solid phase. Three phases or three areas, and then percentage of elements, we already looked at that. When does the first solid crystal form? When the temperature decreases from top down, if you look at the first solid crystal forms at when it goes just below or touches the liquidus line, and when all the material is crystallized, that is the solidus line, or all the and completely it becomes solid. So thing is clear now. So this is liquidus and this is solidus. Okay. Now same diagram, little bit more with an example here. Let's take a composition along this line where you have liquid phase of B, sorry, here it's percentage of B and percentage of A. You have 79% and B you have 21% in this line. Okay. Now on the right side here you have another composition which is 68% of B solid and 32% of solid A, and this is happening at this point here. Okay. So the first case was here. If I take this point, I can say that point has 79% of liquid phase, and because this is my liquidus line, okay, and 21% of liquid B or material B in liquid phase. So both are liquid plus liquid here. and here if I take this point, both are solid plus solid here. Okay, so I think that's clear now. Plus liquid. Okay, now if I take this point here, I will have A and B present, but then I have to look at whether both solid and liquid are there inside that state. Now, that is the tie line. This horizontal dashed line is called the tie line, which connects the solidus and liquidus composition of liquid and solid. Okay. Now, one real example, until now we were talking about schematics. This is a real example from textbook. So, you can see here the blue line, if you follow the one on the left side, you see a blue line here, and same line or similar line I have drawn on this drawing also, on this sketch, and this is the solidus, sorry, the liquidus line, and this is the solidus line. Okay. So, that is also clear now. Yeah. So, you have liquidus, you have solidus, you have liquidus, you have solidus, and so this is 100%, this region is 100% liquid, this region is 100% solid, and this region is solid plus liquid. Okay. So, that is how it is. And now, let us start from the top of this blue line and then move downward, and then let us see what happens when the temperature decreases. So, now look at the temperature, this is 1300, 1200 and 1100. Okay. Now, this particular material, the composition is like, weight percent nickel. So, that is not the important thing here. I am just trying to show you how the phases are different. So, here you can see alpha, the point A, okay, not alpha, sorry, the point A has, all liquid phase 35%. So, that this point if I take, it is about 35% nickel. So, entire thing is liquid, okay, that is this thing here, okay, full liquid. Now, when you reach the temperature, when it comes to, so this was point A is about 1300 degrees the temperature, right, this point here. Now, if I take point B, that is about, let us say 1250, about 1260, 1270, something like that approximately, okay. So, that is the point B, and now this point has, this is the combination. Okay. This is the combination, and you can see that you have liquid phase and also you have alpha phase. Small crystals are actually forming. Okay. The solid phases start to form because you are at the liquidus line right now. So, this is the liquidus line now, liquidus line, and this is the solidus. Okay. So, you are starting to form the solid phases also. Now, this region in between these two liquidus and solidus, this is the alpha plus L, that is solid plus liquid phase. Okay. Now, if you let us say move to the point B, C, now that is this point here. So, the corresponding micrograph or sketch is this. Okay. So, you have alpha and liquid, both are there because it is in between the solidus and liquid. So, both are present. Now, as you move towards D, that is point D, this is the corresponding sketch, and then you can see that the size of the alpha is keep on increasing. You compare with point B, here the alpha is very, very little, and here you have more, more and more solid phase, and as you just cross the solidus, you see that it is 100% alpha and there is no liquid phase in that. So, you can say that this from top to down, if you keep moving, temperature keeps decreasing and then you get to have more and more solid phase and gradual changes. Now, there are also systems where this is an example of two soluble systems or soluble materials. There are also examples where we have partially soluble materials and insoluble systems also. So, that's I thought that's you can read that from this textbook on Mamlok and Zinowski. That's something, a reading assignment. You can read about those two additional phase diagrams. Okay, to summarize, we looked at plane and surface defects. We talked about grain structure and grain boundaries, and also we talked about how these grain structure and grain size, shape, etc. might affect the material behavior. We talked about how they affect the toughness in detail, and also volume defects, which are mainly about the air voids or inclusions inside the material. And then we finally talked about the phase diagrams. We talked about the phase diagram of soluble material systems, the partially soluble and insoluble materials. I request you to go through the textbook. Thank you.